Hello, welcome back to The Effect. We are finally into part 2 of the book. The second half of the book is going to be a little bit more technical, a little bit more focused on actual application rather than just thinking about identification. How do we actually use the tools and designs that are most common for this task? And that brings us to regression, which is the first chapter here, and which is an incredibly important tool and very commonly used tool in causal inference. Now, we already talked about regression before, way back in chapter 4, when we were talking about conditional relationships. If we want to understand the relationship between one variable and another, such as a relationship like how does this variable cause this variable, we are trying to estimate a conditional relationship. As the value of this variable changes, how would I expect the value of this variable to change either as a result or in association or however you want to frame it? That is a conditional relationship. The way that regression approaches the question of estimating a conditional relationship is it says we are going to pick a shape. We are going to describe this relationship using a shape, maybe a straight line, so that as we move along the x-axis, we expect that we'd be moving a certain amount along the y-axis as well as we move along this line. Regression is a line-fitting procedure, where it is you give it the shape that you want to fit, and it chooses the best version of that shape for you. That's what regression does. You can go a bit further even and say, well, it doesn't have to be a straight line. Maybe it's a plane in 3D space where I'm adding some control variables. You can add control variables to regression, which is one reason why it's so popular, because it has that flexibility to add control variables easily, which allows you to isolate just the part of the x-y relationship that is not explained by that control variable. So we've already talked about regression quite a bit. What else is there to say? Well, there is plenty, and there's plenty to go on in this chapter. And the first thing we're going to be thinking about is, well, we've been talking about how we pick a line and we fit the best line that we possibly can. But let's also talk about what we have left out by picking a line. And that's going to turn out to be very, very important to focus on, right? Because the line that we have does not perfectly explain y, right? If we have x on the x-axis, we have y on the y-axis, we would not expect even that all the points would fall perfectly along this line. There's going to be some ups and downs. Maybe there's a data point out here that is a bit above the line. In this case, the reality is a bit higher than I predicted it to be with my line. Maybe there's a point down here below the line. In this case, reality is a bit below where I predicted it to be with my line. These are called residuals. The residual, no matter what method you use to create a prediction, the residual is the difference between the prediction that you made and the actual value that we are looking at, or rather the other way around, the actual value minus the prediction is typically how the residual is written. So we've got this idea of residuals, and in fact, that's what we used to pick a line in the first place. We tried to pick a line that makes the squared residuals as small as possible. But when we're thinking about inference, when we're thinking about trying not just to fit a line, but trying to learn something about the real world from the line that we have fit, we have to not just think about the difference between a prediction and the actual outcome. We have to think about the difference between our model as a whole and the actual outcome. Remember, we are focusing here on the data generating process. We have to do that in order to make any sort of proper inference about what our results actually mean. And our data generating, and just like the prediction is going to leave something out, our data generating process is also going to leave something out. And that is something we're going to give a different name, the error. The error is the difference between what your model would predict if it had all the data in the world and got the best possible version of that estimated model, and what would still be left out. Right? The residual is saying, hey, you made a prediction, it's going to be wrong for some number of reasons. Maybe you left some stuff out of your prediction model, maybe there's some sampling variation, whatever it is. The error term says no. The only thing we're looking for in the error term is the difference between what is in your model and what is still left over. So to give an example about that, let's say that we are talking about trying to predict somebody's wealth using their income. You have a high-paying job, you might expect that person to end up with more wealth. And that would probably be a strong relationship. Probably people with higher incomes are going to end up with higher wealth as well. And so the residual would say, okay, we're using income to predict wealth. You know, sometimes we're going to be a bit above, sometimes we're going to be a bit below in terms of what the actual wealth is. Yeah, okay, that's a residual. We've made a slight, there's something missing there. The error term would say, hey, if income is the only thing you're using to predict wealth, there are other things that also predict wealth that you are not using. For example, perhaps your parents' wealth. Or you happen to win the lottery or something like that, right? Everything that's not in your model is still a predictor of your outcome. It's just not in your model. It has to go somewhere, and that somewhere is the error term. If you look at a data generating process like this one, what we can see, there is an equal sign here. Y equals beta 0 plus beta 1 times x plus epsilon. That's an epsilon right there. Epsilon is something we would typically use to represent an error term. What this is saying is that the data generating process for y, the model, the underlying model where y came from, has x in it. That's a claim that we're making here. And it also has some other stuff, right? X is not the only thing that determines y. There's also other stuff. And that's not just random noise. There's lots of real stuff in there, right? If we are using income to predict wealth, it's not that everything else besides income is noise. We can imagine what some of those things might be, and they're real predictors and determinants of wealth. That is not just noise. And that would include things like your parents' wealth or winning the lottery, like I mentioned. That error term is super important. And when you're using regression, you need to think carefully about what is and is not in that error term in order to be able to make proper inferences about your results. As we go through these videos, we're going to come to a number of assumptions that we need to make about these error terms in order to figure out things that we want. So one thing that we're going to find out is that learning what's in the error term and how the error term moves around is going to be very important for estimating things like standard errors, or the sampling distribution of our ordinary least squares coefficients. But also, on a basic level, when we're focusing on causal inference, a big thing about error terms, and this is one of the most important assumptions that we need to make, is that we need to make an assumption about the relationship between the error term and the treatment that we are interested in. If I want to know the effect of x on y, I need to think very carefully about the relationship between x and whatever is in the error term, whatever is left out of the model. And here we can make a little bit of sort of a linguistic jump, where we've been talking about how to identify the effect of x on y. We've been talking about having backdoor paths. We've been talking about closing things down. We've been talking about closing backdoor paths down such that we can isolate just the causal pathway that we are interested in. Now let's convert that idea to something that is more specific to regression. What does it mean to close a backdoor path down, perhaps by controlling or adjusting for a variable? In the context of regression, that means adding that variable as a predictor in the model, adding it as a control variable. What happens if we go from this model where x is the only predictor to this model where we have both x and z as predictors? Well, if z is part of the data generating process for y, if z was used in the creation of y, then in that first model, z is still there. We can't see it, but it's still there, but because everything that determines y is there somewhere. And if it's not x, it's in the error term. So z is in the error term in that first model. That doesn't mean it's not absent, it's just hidden in the error term. In the second model, when we add z as a predictor, as a control variable in a multivariable regression, we have simply moved z out of the error term into the model itself. This changes the relationship between x and the error term. If z and x are related to each other, well, then in the first model, x is related to the error term. And in the second model, we've taken out some of the part of the error term that x might be related to, and maybe at this point, x is no longer related to the error term. So here's that linguistic jump that I mentioned. We've been talking about closing all the back doors in order to identify the effect of x on y. In a regression context, that is very, very closely related to the idea that we have made it so that x is unrelated to the error term. And this is an important assumption that we need to make if we are doing some sort of causal inference with a regression model. Because if x is related to the error term, then we will face something called omitted variable bias, which is largely a similar idea to saying that the effect is not causally identified. Omitted variable bias, we might say that x is endogenous if it's related to the error term. There's a bunch of different terms that are used here, but the basic idea is this. If we have omitted from our model a variable that is related to x, right, that's the omitted variable part, as in this first model where if x and z are related to each other, but z is in the error term so that we know that x and the error term are related, that will bias our estimates. The estimate that we get will not be reflective of the actual causal effect of x on y. We have not identified the effect. Why is this? Why does omitted variable bias occur? Well, you can sort of imagine the sort of issue that ordinary least squares is going to have. If we just look at the relationship between y and x, right? But we have z over there, and z is related to x. But in this first model, we haven't told ordinary least squares about z, right? It doesn't know. It can't do anything about that. So let's say, for example, that z is positively related to x. They're positively correlated. And also z is positively related to y. But we still estimate this first model where z is in the error term. What's going to happen? Well, z is doing all sorts of positive things for y, but y doesn't know about it. But y does see that x happens to be around when all those positive things are happening. So it will give x the credit for all the stuff that z did, right? Z is doing all this stuff. Y doesn't know that z is doing all this stuff, but it does see that x happens to hang around z, and z is doing all that stuff, right? So it will give x the credit. This will be the bias, the omitted variable bias part. The ordinary least squares will assign the effects of z to being the effects of x, because it doesn't know any better. So When we have a regression model like this, we need to think carefully about the error term. We know that all the variables that are in our model that we're actually using as predictors in our regression model are in the model. Those are being included as predictors. If we're interested in the effect of x on y, and we know that there are backdoors to close, we can close those backdoors by including control variables in our regression model. Including a control in a regression model is a way of closing a backdoor that goes through that variable. This means we need to think carefully about what is still in the error term, what is in the data generating process that has not been included in the model. If that error term includes stuff that is related to our treatment, then we have omitted variable bias, also known as x is endogenous, also known as we have not identified the effect, also known as we have not closed all the backdoors. When this happens, we simply have not identified the effect, as I mentioned. The coefficient on x, when predicting y, will not reflect the causal effect of x on y, because ordinary least squares will mix up the effect of x on y with all those alternate explanations that are still in the error term. It will give x the credit, or the blame, for whatever the things in the error term are doing if those things are related to x. So as we move forward with dealing with regression, there's a lot of stuff that we're going to have to think about, a lot of which is going to do with that error term. Some of which is going to have to do with how much sampling variation we have in our coefficients. Some of it's going to deal with how we can relate the regression model that we build to the causal identification that we are trying to make. And those are all things that we're going to be covering in this entire chapter's worth of videos. Thank you.